Now this is seen in the B model traditionally. Now I can see this directly on the elliptically solved Claudial using homological mirror symmetry. So we'll see the SL2 acting on the derived cascade. Language, but this I could be doing the Gromov-Litton partition function, the stable appearance partition function, the Hydro-Climate promise, the normalized Donaldson promise invariance frequently to go and think of this or just the topological string partition function. This is the object I want to understand in these variables. So in the good variables, that we have already shifted, and I'll keep on using Q. That's why the tilde is now off. These are the variables I want, not the large radius variables. Q is the usual exponential 2 pi I tau. Capital Q is this, and lambda is just Z is just a multiple of string coupling to go ahead and match the theory of Jacobi forms. We factor out the degree 0 in the base contribution and express everything else in powers of the base degree. All the private degrees contained here. So what ZZ contains is topological string amplitudes for all classes of all genus where the projection to the base is degree Z. After correcting for the degree 0 term. After factoring out that contribution. And our claim, as you can see it, is that this quantity is a weak Jacobi form of wave 0 and index D times D minus 3 over 2 with multipliers in the sense of x74. That's the main claim. But more precisely is that we can go ahead and give a finite convex for this form. So the denominator is a fixed form. This is a fixed Jacobi form. It is known. And this is a weak Jacobi form of a certain weight and a certain index. I'll define weak Jacobi forms in a second. And the point is that this lives in a finite dimensional vector space. So we reduce the entire topological string amplitude, at least at degree D, to a finite problem. And I will say that there was a time when we were really hoping that there would be no limit to how far we can take D, but sadly that's not the case, and the field is still open. Okay, and so this is not the first time Jacobi forms came in related situations. So the elliptic genus of E-strings has been studied for the last few years by Hadi Vatha, Kim Kimley, Clark and Vatha, and Kai Langdon 7. And then Hadi Vatha and Vatha studied this in systematic superconformal field theory in a related situation. These came up. As a consistency check is that we have in the holomorphic geometry, all you see are holomorphic expressions, which are not modular necessarily for the CE2. If we replace that by the almost holomorphic modular form E2 hat, where tau 2 is the imaginary part of tau, and we take the Z and replace it by its non-holomorphic part, of which this is the holomorphic limit, then this, just assuming that the partition function is expressed in this way as a Jacobi form, automatically implies that this satisfies the modular anomaly equation of Boeing, Shadowberry, Dial, and Rajot. So this is a nice consistency check that the ansatz automatically satisfies the fiber version of the holomorphic anomaly that had been studied before. And in the recent work, the new stuff not yet written up, is that we can now derive the modular anomaly equation directly from the wave equation, wave function version of the holomorphic anomaly equation due to Whitten. So I mentioned we'll talk about this, so I'll be brief on this subject. So just quickly, what Jacobi forms are is that we have two variables. We have a tau variable and an elliptic variable, which lives modulo the lattice given by 1 and tau. We have SL2 Z transformations, and Jacobi forms act in this way. So K is the weight, and M is the index. So weight 0, this term is gone. It's just a modular form. So you already know lots of Jacobi forms. When we have Fourier expansions, because we have previously both in tau and in Z, so Q we've already done, it's e to the 2 pi I tau, we have a Fourier expansion there, we suddenly have e to the 2 pi I Z. And you'll see, remembering that 2 pi Z is lambda, Y is e to the I lambda, e to the I lambda, which is exactly the parameter of Donaldson Thomas theory or stable pairs theory. So this is the same change of variables that you would know if you're doing enumerative geometry. It's the same one that comes up in the string setup. So a weak Jacobi form is not only, it's that when you go ahead and write this in terms of the Q variable, it stays holomorphic. So there's a condition at the cusp. No condition on Y, but we have a condition at the cusp in Q. That's a weak Jacobi form. Phi minus 2, 1 I just wrote down. This is a well-known Jacobi form of weight minus 1 in index 2. Another one of weight 0 is 1 is half the elliptic genus of K3. And the basic result here is that the weak Jacobi forms form an algebra migrated by weight and index, and the algebra is being generated by E4, E6, Phi 0, 1, Phi minus 2, 1. Which means that if you go ahead and just pick a weight and an index, there's only finitely many polynomials in these expressions you can write. So that automatically proves that the spaces of Jacobi forms with a certain weight and index are a finite dimensional vector space. Okay, so let's look and see what this means for D equals 1. So phi 1 of tau Z is supposed to have weight 16 and index 0. Index 0 is a modular form. So we're just looking for modular forms of weight 16. There are many of those. two-dimensional vector space. So what we have to do is to find this partition function is just determined by two invariants, two geometric invariants. Just calculate two numbers, the whole partition function for every curved cross every genus that projects to a line. So